there is a Schrödinger equation for wave function. There is wave function free quantum mechanics when we go into matrix elements, right? No. When I was declaring this idea, I saw non-verbal confirmation from Bill, like telling that he was sharing it. Good. When we convert Schrödinger equation into matrix form, we get rid of wave functions, right? So it is another thing. Quantum mechanics without wave function. And what's the third way? I try to be careful with fingers so that everything is public. Who was not opposing, but like competing with Schrödinger?
Heisenberg?
Yes. So what was his main idea? Its main idea why he is glorified in textbooks, but practically why he is successfully competing with Schrödinger. Let me remind.
Huh? Easier?
Easier, but what is easier?
Like the computation, or just like the calculations, or
yes,
because you're not taking the derivatives, or no, you're
excellent.
Forgot what word. Yeah.
Yes, D1 plus 1 for sure. So he told everything, like radio lecture, skipping only the title of this mini lecture. So Heisenberg equation of motion. But all values and principles were declared. So there is a way to solve all quantum mechanical problems, which means predict outcome of observation without wave function, without matrices, just by algebraic operators and equations of motion for observables. Right? So it's the title for this chapter is Heisenberg equation of motion. But if you practice Heisenberg equation of motion for real life, you need. You remember this Heisenberg equation of motion includes a commutation between Hamiltonian and operator corresponding to observable. Yeah, haha operator. And if we will go this way, we will need to compute Hamiltonian with some different operators again and again. Right? So it is a practical skill. And if Hamiltonian and an operator commute, then there will be no change in time. Heisenberg equation of motion will predict that expectation value will be the same if you repeat measurement again and again. But if they do not commute, which is very typical, then there will be some interesting dynamics. So commute means swap. And often swap of these matrices gives non-zero matrix. There is a big challenge for any instructor of quantum theory, and some of you will become instructors. You need to teach or at least TA. So it is counterintuitive theory, as you already realize. Right? And this commutation is one of the counterintuitive concepts. On other hand, we always want to get through like understandable things, distribution center where particle is located as position and momentum. So this conversion from functions, position, momentum to more abstract operators and matrices is always hard. And you are my heroes because you are surviving this. So it is not easy. The fact that we are not yet super perfect on commutations is okay, and we will go through this concept again in a couple of weeks when we will go to next class of systems. So when we will depart from harmonic oscillator, we will go to so-called spin and angular momentum that I promise that we will complete. If time allows, there will be more chapters. But spin and angular momentum will be included. And there will be also operators which can be represented as matrices, and there, especially for speed, matrices will be simplest possible matrices, 2 by 2. So there we will have a chance to practice a little bit more commutation. Just giving you a little heads up what is going on. So soon we will complete harmonic oscillator, and here will be angular momentum and speed. Whew. So right, we did agree, and I do not withdraw my word that the submission of this homework will be on Wednesday, right, 14th. But if you have Steam, especially as a group, to it earlier, we can get bigger credits. And why I'm a little worried about doing this earlier, if possible, because there will be another homework which we need. I have certain amount of homework to stick into the course, and likely it will be due on the Friday next after this 14th. So 14th one homework, and then 16th another one. And if we stick too many things at short time, it will be hard because you are super busy and some of you take 20 credits. So consider completing it earlier. If as a group would be perfect, but even individually, just leave you more space, more time for next thing. And as you can recognize, here will be your favorite operation of commutation. Whew. So this is the last slide from Wednesday, when we met on academic matters, not for presentations, right? Diagonal operator. So if the system is left alone, and here we are focusing on harmonic oscillator. So if the system is left alone, if it is diagonalized, if we are speaking in the basis of eigenstates, then Hamiltonian should be diagonal, right? So it is a matrix where diagonal elements represent eigenenergies. Yes?
So on that diagonal matrix, it's supposed to be k plus 1/2, right?
Yes.
So then why is the first element just 1/2 and not 1?
We start counting from 0.
Okay.
Okay. So if we are if these matrices are expressed in the basis of eigenstates, then Hamiltonian is diagonal. It's very standard, and sometimes it is boring. If you start when later on, some of you will start solving true problems. The non-diagonal elements in Hamiltonian is what makes life interesting, and what it comes from challenges from nature. But right now we are in this academic, and there is a frequency times time constant up front. So these two notations are equivalent, right? So this converting element k into element number k, like, do not moving occupation from certain orbital, from certain eigenstate. So we start with k and end with k. Symbolizes diagonal methods, right? So if you would convert from diagonal to subdiagonal, it usually k to k plus 1 or k to k minus 1. If it would be everything will be populated, we would just write m, k, and then here will be non-zero matrix elements. Good? Well, you can give this answer just looking at the matrix, and you probably got it before, right? And we discussed it. So the lowest energy of harmonic oscillator is not 0. It's half of the frequency times Planck constant. But we will go through it more like an exercise, how to extract the value of this energy if we have the operator as matrix or operator in Dirac notation. The second half of the lecture will be introduction of new section about harmonic oscillator. You may protest, object, and tell, why do I need foreign equations? Why do I need to suffer mathematical derivations if we do have a code that predicts solution of any one-dimensional quantum problem? I have already seen, I'm just sitting on this, we have already seen presentation by Isaiah, who is not here, but he was really helpful on Friday. When the Gaussian distribution away from the center of harmonic oscillator starts moving back and forth, and in addition, its shape doesn't expand infinitely as it was in free space, but it oscillates. Or if we select it right, it will be just not changing. So some of you answered this last question correctly in the homework. Yes, if you were thinking this way, nothing is wrong. But what will you do if, after finishing the class, someone will challenge your skills in academic knowledge, or if you really need to go to next level courses? What if there will be a problem that is not solvable, and instead of what is if it will be not one dimensional? What if it will be some additional interactions? So if we will need to depart from comfort zone, then we will need a little of additional mathematical muscles and background in the course material. So practically, in the cage of this course, whatever follows can be done by running this MATLAB code. We will not get big discoveries completely, but if you are not standing up and living, it means you are investing into your future and into a little more solid knowledge. So we are going to reproduce things that you have already seen, but from more fundamental, rigorous point of view. And the second part of today's meeting will be devoted to this next section, that as a result, so this next section will be dealing with pen and paper, mathematical prediction of the future for harmonic oscillator. You already know what it will be. Right? The wave packet, if it is a wave packet, will move backwards and forwards. But can we get it as an answer by pen and paper? From which principles, through which equations it goes? So, and the shortcut will be done through initiation period. So we will try to find eigenstates with eigenfunctions of annihilation period. And if we get success in this question, the life after that will be a little bit easier. Makes sense? Or not quite? Okay. Is this thing a big surprise for anyone? Well, let me ask you a gentle question. Give me a secret sign if the writing on the board is surprising. Give me a little sign if you are not sure. Maybe surprising, maybe not. Okay. Give me a sign if it is basic alphabet that you understand and confirm. No. Okay. So even if we do some operation with operators, some smart operation with operators, and we get writing on a paper that looks like a number. We do operations with metrics and get a number. This is not possible. Even if we forget to put a little head on the top, if we do operation with matrices like subtracting, adding, commuting, the result should be a matrix. And if we tell that it is like matrix equal to a constant, we should understand that it is a constant multiplied by identity matrix. What is identity matrix?
Diagonal of just ones.
Yes. Who would protest that it is a good representation of identity matrix? Okay, who would confirm that it is his or her favorite way to represent identity matrix? No? So, look, if you have basis state or vector number k, it converts it to k. Wait. Oh. This is the first time I'm writing anything. So, if we have element number k, right? And we do have 1, 1, 1, 1, 1. Here will be zeros. 0, 0. I'm tired of this code. So if you do have row by column, then by multiplying this row by this column, so if we do have only zeros in this row, no matter what is above or below, it will be 1, right? And it will be placed on this side, number k. Make sense? Or if here we have constant k, k here. If you have diagonal matrix, it will reproduce the same vector. Multiplying diagonal identity matrix on any vector, you will get the same vector, right? No novelty. But reproducing, meaning you converting element number k into element number k with coefficient 1. Or you can convert element number 0 into element number 0. You convert element number 1 into element number 1. You convert element number 2 into element number 2, and so forth. So this is Dirac notation, representation of the identity matrix. Good? And if we will define this matrix in MATLAB and plot it, it should look like little sticks coming out on the main diagonal, and then there will be nothing away from the diagonal, right? So if you define identity matrix and plot it, it will be like a city center and suburbs. Good? So if you practice commutation of position and momentum, when it is expected to get identity matrix multiplied by constant, then it should look this way. Okay? Good. So what about sandwiches? What is ground state of a system? Not only the harmonic oscillator, but any system.
Basement.
It's very artistic, but more rigorous. Well, let's express ground state in a fancy way.
The lowest energy possible for the lowest state.
Okay. No, that's not wrong.
Lowest potential of the system.
Lowest potential of harmonic oscillator can be, is 0, and lowest energy is 1/2 h per omega. So it's not lowest potential. Lowest energy, good. Lowest potential just brings us in the right direction. But let's think as crazy theorists. Completely mathematically and algebraically. Of course, you are theorists now. So, again, what is energy of ground state? Suppose that we know Hamiltonian and we do know the wave function of ground state, or we can use this Dirac. So the lowest energy will be matrix element of Hamiltonian between lowest wave functions, lowest eigenfunctions. If Heisenberg equation of motion was operated, then this is oh expression. Easy to remember. Energy oh Heisenberg aha. So matrix element of Hamiltonian for ground state wave function. Right now, we all, not only you, but I myself also, we are kind of exhausted and tired of the lots of material, and maybe it's not the right time to advertise your new course, which will be on the spring break. If you elect and decide to go into computational chemistry, you will see that this approach to the lowest energy of the system is very genuine, not only in physical chemistry, but in other branches. Whew. How does it apply to our today's life, to our chapter on harmonic state? Can we practice? Can we? This well, it's not actually O is 0, but how are we going to practice this definition? Do we have matrix for Hamiltonian? Do we have wave function? Right? So this phi naught, we can write it that it is 1 in the lowest state and then zeros in all others. Basically, what I'm going to do is, if I flip here, just need to do this. If I put my Hamiltonian, so it's Hamiltonian, and then I put row and column 1 0 0 0 1 0 0 0. Omega. This will be practicing of the definition for finding eigenenergy. So here we have Hamiltonian, and here we have wave function as bra and as ket. There is no wonder that this operation will parse. Will parse which element? Yes. So by multiplying multiplying this row by this column, you get a vector which has 1/2 in the first element and zeros in others. And then we will multiply this row by remaining column, and then it will parse only this element 1/2 times h bar o. Right? Bless you, bless you, bless you.
Thank you.
Make sense? Not very challenging. So finding eigenenergy is just parsing the first element in the matrix, if the matrix is known. So how do we do it in Dirac's notation? Easy. If the questions are trivial like this, Dirac notation is not needed. But if we are getting multiplication of several matrices, if you get something really crazy, Dirac notation is, becomes 100 times more efficient. So it's a way to multiply matrices in one line. So here is our Hamiltonian harmonic oscillator in Dirac's notation, right? Identity matrix, this growing element, and we adding 1/2. And in order to practice our definition of eigenenergy, we make a sandwich. Wave function, operator, wave function. So how should we interpret this 1/2? Is it really a number? So operator cannot be equal to a number, right? So anytime lazy writer forgotten to give explicit value, it means the author trusts the reader that we understand. As soon as it is declared that it is operator, any constant should be interpreted as identity operator. So here we should understand that it is summation k, k, k. If I do not start the second chapter, then it will be really relaxing. I do not have a defect of speech, just there is no other letters. K, 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 plus 1/2. K, K. It's natural to put this KK outside of bracket. So I'm not doing anything non-trivial. It's just rewriting the same expression from different aspects, from different points of view, right? So if the indices in ket and bra are the same, it means it is diagonal matrix, and here are the values. So it is will be For k equals 0, it will be 1/2 h bar omega. For k equals 1, it will be 3/2 h bar omega, and so forth. So it is our Hamiltonian operator. Now we do want to multiply left to make sandwich, to multiply by 0 from left and right. So, 0. 0. In some sense, intermediate goal while reading true problems in quantum theory is to eliminate wave function, right? Because wave functions are not measured. Anytime when we go to observable, we eliminate wave functions in one or other way. And in other technical aspects, we also become happy while eliminating wave function. What is the main principle that helps to avoid it, to get rid of wave function? Which property of eigenstates?
Orthogonality.
Yes, but which means?
Which means that if the indices match it, the product of them is 1.
And do not match,
B equals 0.
right? Everyone agrees. If you want to follow Dirac notation, it will be like Km will be 1 if k equals m, and will be 0 if k is not equal. How do we use this rule into our expression? Like k bra k cat 0. Bra. How should we interpret this bra? According to Ben, according to orthogonality relation. So the k is eigenfunction of arbitrary number, and 0 is also eigenfunction of number 0. And this writing, it is the same as integral. So if you believe that, it should be either 0 or 1. Right? So what will it be? Will it wish to answer?
Will the diagonal matrix with the first element is 1 and the rest is zeros?
Yes, but you can, yeah, correct. So if k equals 0, it will be 1. If k is not equal to 0, it will be 0. And delta 0. So we should keep only those values when k equals 0. Now, look here. Here is another bracket. Black bracket. Black and cat. Right? So this sandwich multiplication of Brian cat from left and right has an order to convert matrix, Dirac notation matrix, which is like cat and bra. We put additional Brian cat from the front, and it converts into 2 convolutions, into 2 orthogonalities. And we get rid of wave function twice. So here we replace the stuff by delta k comma naught, which means k must be equal to 0. Here we have also this bra for 0 wave function and cat for k wave function. Should it be something different or same result? It will be delta 0k. So it will be non-zero only if k equals 0. For all other elements, it will be 0. Which two animals are we going to remember? Yes. So who will be snake? Yeah, and bunny will be the delta function. We are a little ahead of this holographic notes. Which 0, 0, summation, delta, delta. No. Well, we have this delta 2 times, but it is the same. So their product will be same delta. So this snake and this bunny, or these two bunnies, will result into removal of them both and keeping only such value of this line where k will be equal 0. Equal 0. So what will be the result?
1/2 x.
Yes, sir. So energy of any state of harmonic oscillator is 1/2 frequency times time constant. This answer is known for anyone who took physical chemistry, but snakes and bunnies are known only to you. And Dirac notations for matrices is an upscale tool and skill that can be used for more complicated problems. So we applied it to something simple, but later on we will have it's really strong tool to get through challenging things. So definitely we do not have time for a second section, which I will postpone. But let me mumble something about general idea. Did you watch historic adventures movies? I don't remember which one because in the teenager was just watching them continuously without memorizing the names of movies and characters. But it was a like pattern when the character that we are emphatic to needs to save someone in the like castle or tower, and when a person needs to penetrate into like this high tower. I saw this trick. I don't know if anyone can do it in practice. So if a person holds the anchor, throws it, and then tries to climb on a rope.
It's the Batman.
Definitely Batman.
Well, this is a repeating pattern. It's in several stories. I saw it from movies from 30s and in recent movies as well. So we are. I know no one likes to remember the past because we are predicting the future. But in the past, we were making axes, like methods and systems. Right? On one hand. On another hand, we always trying to predict the future, which means to set up initial wave function and look how it will change in time, with understanding that wave function is not what we need. What we need is observable. In your homework, you gave examples of observables and how they encode. So if instead of MATLAB code we want to solve such problem of non-equilibrium, and this formulation of predicting the future is interesting only if initial state is not an eigenstate of Hamiltonian, is not a stationary state. If we start from stationary state, nothing will change. Remember, once it was when we studied one-dimensional box, we made a superposition 50-50% of ground and first excited state, right? And then we let it go and saw that the wave packet oscillates force and back between walls, and expectation value of position also oscillates. So what if you want to do the same thing for harmonic oscillator? You kind of know that you will see this pattern. If there are walls, there will be reflection, so we will see oscillations. And we already saw it through MATLAB code, but how can we approach it from pen and paper? This is a challenge. You remember how that eigenfunctions of harmonic oscillator are relatively complicated, right? Like polynomials times exponential. The eigenenergies are not complicated, but if you would put all these things into our machine to predict future, are we sure that we will be able to process it? It will be like a big collection of equations that are hard to process. So what I'm going to offer, well, not today, but next time we meet, is a mathematical tool that will help to solve this problem, to see what will happen for non-equilibrium state. And this tool is our anchor. And the name of this anchor is coherent state. Coherent state. And the coherent state is an eigenstate of annihilation operator. So if we make another mathematical exercise and try to find eigenstate of annihilation operator, in a couple of meetings, it will be really easy, well, much more easier than otherwise, to find the non-equilibrium motion of the wave packet in harmonic potential. Without this tool, without this anchor, we will not climb this wall. Okay? So motivation is find eigenstate of harmonic oscillator. I really wanted to present it today, but time is over. So I hope to see you on Wednesday. If you have time, try to focus on the homework a little bit earlier so that later on there will be more time for other things. Meeting is done. I will stay here to answer questions if any.